Raw milk exists as a complex chemical system, an oil and water emulsion, where liquid butterfat is dispersed as discrete droplets within a continuous aqueous serum phase. These native fat globules measure between 2 and 6 micrometers in diameter, though their size varies. Because butterfat is less dense than the surrounding plasma, the globules naturally float toward the surface. Left untreated, this gravitational separation creates a distinct, visible layer of cream at the top of the container within a few hours. To achieve long-term shelf stability, processors must permanently alter the physical structure of these fat globules to counteract their natural buoyancy. Industrial dairy processing achieves this stability through purely mechanical intervention, preserving the milk's original chemical composition. High-pressure homogenization is the universal industrial standard for this process, utilizing massive stainless steel equipment to enforce uniform consistency. The equipment's primary objective is the subdivision of those native fat globules into particles smaller than 1 micrometer. By applying macro-scale fluid dynamics, specifically intense turbulence and shear, the system forces the microscopic particles into a state of physical stability. The homogenizing valve assembly contains the precise disruption zone. All particle size reduction occurs here, within the gap between the forcer and the valve seat. A positive displacement pump forces the fluid into this narrow restriction, at static pressures ranging from 10 to 25 megapascals. As the fluid passes through the 0.1 millimeter gap, this stored pressure converts into kinetic energy. The velocity of the milk spikes to between 100 and 400 meters per second. These velocities generate intense turbulent eddies. When a high-speed microwhirl hits an oil droplet of similar size, the shear force tears the droplet apart. Simultaneously, the sudden pressure drop causes cavitation, the formation of localized steam bubbles that violently implode. These implosions generate shock waves that further fracture the fat droplets. An impact ring positioned downstream provides a secondary stage for disruption, where the high-velocity fluid undergoes further particle collision. The assembly functions as a restriction designed to maximize kinetic energy transfer. Delivering fluid into that microscopic valve gap at industrial flow rates requires significant mechanical infrastructure. This is the cylinder assembly, a heavy-duty pump block that utilizes a positive displacement system to generate the necessary process pressure. In the drive assembly, an electric motor rotates a crankshaft, which uses connecting rods to drive 3 to 5 reciprocating plungers. Spring-loaded inlet and discharge check valves maintain a strict one-way flow, ensuring volumetric efficiency as the plungers displace the fluid. The dynamic plunger packings must meet extreme material tolerances to prevent blowouts under cyclic loads that often exceed 400 bar. Internal oil lubrication systems and heat exchangers protect the main bearings from the heat generated by these continuous mechanical forces. The machine's physical scale is dictated by the structural integrity needed to safely convert high motor torque into extreme fluid pressure. Mechanical pressure alone is ineffective if the fluid's thermodynamic state is incorrect. Milk must be preheated to between 55 and 80 degrees Celsius. This ensures the butterfat is completely liquefied, as solid fat crystals cannot be effectively sheared. In high-fat products, newly shattered globules have a tendency to collide and fuse back together, a process known as re-agglomeration. This clustering can result in a highly viscous cream plug that compromises the consistency of the final product. Processors resolve this through two-stage homogenization, placing 2 valves in series. The first stage applies the primary 10 to 25 megapascals to achieve the initial disruption of the fat globules. The second stage applies a lower back pressure, around 2 to 3 megapascals, to break apart any newly formed clusters and control the cavitation from the first stage. This configuration grants precise control over the final viscosity and rheological properties of the emulsion. Immediately after exiting the high-pressure valves, the processed fluid now consists of a dense dispersion of perfectly uniform spherical droplets. The fat globules have been reduced to a diameter of less than 1 micrometer. This size reduction results in a 4 to 6-fold increase in the total surface area between the fat and the plasma. The original globule membrane is no longer large enough to cover this massive new surface area, leaving the lipids exposed. Plasma proteins, specifically casein micelles, spontaneously adsorb onto the new fat surfaces, forming a thick protective shell. This mechanical disruption initiates a biochemical reassembly, forging a permanent membrane that locks the fat globules into their stable submicron state. The process spans from the rotation of a macro-scale motor and high-pressure pump blocks to submicron fluid dynamic shear. This trajectory provides structural uniformity and permanent shelf stability without the use of chemical additives. High-pressure homogenization stands as a precise application of fluid dynamics, where extreme physical forces are used to dictate the microscopic structure of a liquid.